Alright, ladies and gentlemen, so as we wrap up 6.3, our goal of this video is to kind of look into, I should say kind of, it is to look into specifically finding the antiderivative of the natural log of x. So it's kind of interesting when you think about it, because we use the natural log of x as u so many times when we're doing integration by parts. But the reason why we don't usually want to make it dv is because the integral or the antiderivative of natural log is not an easy thing that's on the top of our tongues that we know kind of all the time. And so within the video, we're going to actually take the integral of the natural log using by parts, all right? And then we're also going to show an example of anti-differentiating the sine inverse of x. So let's take a look first and foremost of using by parts. If you remember correctly, Lipit, the first L, is saying, hey, can we use a natural log as our u? It's our first goal. So let's go ahead and make u the natural log of x, just like we would if it was part of another by parts problem. And so that only leaves left dv to simply be dx, right? I mean, think about it. That's all that's left is the dx, and whatever dv is going to be. But that's not a terrible thing, because then you've got to think to yourselves, all right, well, what is du? Well, the derivative of the natural log, so du would be 1 over x times dx. And then you're thinking about what is the integral of just dx. Well, I'm going to throw a 1 in there, right? Because technically there is a 1, and the antiderivative of a constant is just whatever the differential is. And so that would be just x. So v is going to equal x. So let's go into our by parts formula. So it is true that the integral of the natural log of x times dx is going to equal u times v. So I'm just going to go ahead and make this x times the natural log of x, and then minus v du. Well, that would be v times du. So minus the integral of 1 over x times x dx. Well, what happens here? Take a look. X's cancel out. The integral of 1 is just simply going to be x. So x ln of x minus x, and then plus our c for our constant of integration. Now, this antiderivative of the natural log is going to come up a lot in future problems, okay? If you can almost use this as a rote memorization to help you on out as we go through, I'm telling you, it's going to be very, very beneficial. Natural log of x, antiderivative, x natural log of x minus x. And it's going to kind of help out. I promise with some more practice, it'll come almost second nature to us as well. All right. So let's look at an example of finding the antiderivative of a inverse trig function here. So we want to take a look at an inverse trig function, and we're going to use the example of finding the integral of the inverse of sine. Inverse of sine, if I can get this to right at all. I apologize, guys. Alright, the integral of the inverse of sine x dx here. Alright, so this is another interesting one where we don't necessarily just have the basic antiderivative of the inverse of trig functions. And so instead, we need to kind of focus it as a by parts. Because think about it, if you went ahead and you made this a u substitution problem, you might not get very far, okay? You might not get very far. You know, you can play around with some trig identities and see if you can kind of get to where it's at, but this is a great by parts example because it's actually very simple to find the derivative of an inverse trig function. And so let's kind of go into that. Remember what lipid is. Lipid goes natural logs, inverse trig to make u. So we're going to make u the inverse trig function because we can easily find the derivative of sine inverse of x. Okay? We've done this before. So dv then would end up equaling just simply, once again, whatever is left on over in dx. Alright, in dx. Wow, this is not writing at all for me today. Alright, so dx. I said dx. I apologize for how bad it is writing. Alright, so let's kind of continue to push on forward. Now we have u, so du, no, we want to find du in this particular case. Well, the derivative of the sine inverse of x is just going to be 1 over the square root of 1 minus x squared. That's kind of just one of our identities that we remember. So 1 over the square root of 1 minus x squared. And we can go back and look at our inverse trig derivatives if we need to, okay? So times our dx. And then v, once again, is going to just equal x. Alright. So let's keep pushing along. So now we have u and v, and du and dv. And so let's just throw it on into our substitution that we have. So let's take a look. So pushing on forward, we have u times v, so that would be u times v. So we have x times the sine inverse of x, sine inverse of x, and then we have minus the integral of vx times du. Well, 1 over square root of 1 minus x squared is du, so I'm just going to throw that over 1 minus x squared times dx. Okay? So, we're starting to get somewhere a little bit. We're starting to push forward, all right? But how can we possibly go about getting the integral of x over square root of 1 minus x squared? Well, hopefully you're noticing that this is a good opportunity for u substitution. Alright, so we're looking for a u inside of this integral of x over 1 minus x squared, right? We're trying to find a u that's going to work in our favor. Remember, when we're trying to find a u to fit into our favor, guys, we're really just trying to make sure that we're constantly choosing a u that's going to leave us with a derivative that is still found inside the integrand itself. So I think for our best bet is to probably go ahead and make that u 1 minus x squared. So let's make that u equaling to 1 minus x squared. And then when we take that derivative, du is going to give us negative 2x times dx. Alright, negative 2x times dx. Alright, so let's continue to look and see what we've got going on here. So now we need to basically kind of take into account another possible integration by using u substitution that we've got into here. So let's continue to look into this. So if I have my negative 2x, think about it for a sec. If I have negative 2x in there, and I currently have an x up top right now, basically I need to take into account for that too. So I'm going to multiply it by that 1 over 2, right? I'm going to make a 1 over 2. But I'm going to keep it positive. Right now it's a positive 1, so I'm going to keep it negative 1 over 2. And so kind of going through our u substitution right here, this is going to look like x times our sine inverse of x of positive 1/2, because positive 1/2, right, negative negative makes positive, of the integral of u to the negative 1/2 power. 1 over, right, the square root of u, or 1 over u to the 1/2, and then du. Okay? So then we have our du in there as well. That looks terrible. Hold on, let me try to erase this and get an actual u. Alright, so we got du. Alright, so now we're making some strides. So now let's integrate u to the negative 1/2. Alright, well if I add 1, that's going to leave me with negative 1/2 plus 1, or 2 over 2. So that'll end up giving us a positive 1/2. And I divide by that 1/2, we're going to end up canceling with our 1/2 that's out here right now. So let's take a look. What happens? We end up getting left with x times sine inverse of x. The 1/2s cancel when I raise the power. And so I'm really just left with plus u to the 1/2 power, and then plus c. And the last thing I need to do is just to make sure that I substitute my u back on in. So this is x times sine inverse of x. And then we're substituting our u back on in, so we're going to finish on off with plus the square root, or you can leave it to the 1/2 power, it's really up to you, 1 minus x squared, and then there's our plus c. Alright folks, so that's going to wrap it on up for us, integrating the antiderivative of sine inverse. Alright, integrating inverse trig functions by parts. On to the next one.